Hey class, welcome to our classy and informative video on the exciting topic of the recrystallization of cartridge brass. Please keep your eyes peeled and your ears open for a journey of science and metallurgy. Let's begin. Section 1. What is recrystallization anyway? Well, before we talk about recrystallization, let's take a step back to figure out why it's important. When we plastically deform a metal, a small percentage of that expended energy remains stored in the metal in the form of increased internal energy. As a result, changes occur to the material's physical and mechanical properties. Overall, there is a notable increase in hardness and tensile strength with the proportional amount of cold working, as you can see in this diagram. On a microstructural level, this increase in internal energy from plastic deformation is associated with an increase in the dislocation density, as well as the density of point defects such as vacancies and interstitials. Now, as we can see in this rolling diagram, the grains become elongated in the direction of cold working and heavily distorted. This distortion is evident from a bending of annealing twins. So, while the increased hardness and strength that result from the cold working operation can be important sometimes alone, it's often necessary to return the metal to its initial condition by annealing. This usually means holding the cold worked metal at a temperature above about 1/3 of the absolute melting point for a period of time. The annealing treatment is divided into 3 distinct regions. The first step is recovery. This usually occurs at low temperatures and involves the motion and annihilation of point defects, as well as the annihilation and rearrangement of dislocations, resulting in the formation of subgrains and subgrain boundaries. A distinctive feature of this recovery process is that it does not involve any change in the grain structure of the cold-worked metal. The only changes taking place are the dislocation arrangements within the existing grains. Now, finally, we have recrystallization, the step that occurs after recovery. If increased thermal activation is available, so for instance, if the temperature is raised, nucleation and growth of strain-free grains in the deformed matrix will take place. Now this is important. As these grains grow, the dislocations in the matrix are annihilated at the boundaries of the newly formed grains. Strength and hardness decrease considerably, and ductility increases.
Now, we will be talking about the importance and some applications of recrystallization and annealing. Recrystallization in general. Annealing a material can decrease its strength and hardness and increase its ductility. Annealing causes all new stress-free grains to form, which effectively resets the material for work hardening and use. Because all of the grains are new, this removes traces of cold working and work hardening within the material. Annealing softens the material and makes it more malleable, which in turn makes it easier to work with. Additionally, annealing can improve the magnetic properties of certain materials. There are many applications for annealing and other heat treatments. One annealing application for steel would be the final step for larger repairs. Say for instance a steel part fractures. While welding can be used to repair the macrostructure of the part, this welding can also damage the microstructure of the steel and in turn change the material's properties. By annealing the heat affected zone, the material properties can be fine-tuned and be made consistent with the rest of the part. These 3 images along the bottom show a laser seam welded S30403 stainless steel. And on the left shows 0% recrystallization, in the center 50% recrystallization, and on the right total recrystallization. The rest of this presentation will deal primarily with the recrystallization of C260 brass, commonly referred to as yellow brass or cartridge brass, composed of 70% copper and 30% zinc. Annealing of cartridge brass is extremely important for ammunition. To produce the shape of a casing, the metal must be bent into shape, This work hardens a brass at the neck of the casing. The neck is annealed to be more malleable, so when firing it assists the bullet chamber and can assist with expansion as the bullet is fired. Additionally, once a bolt is fired, the casing can be reused. This is called reloading. By once again annealing the neck of the casing, it becomes easier to set a new bullet inside of the casing, and reduces work hardening in the casing from being fired, which extends the lifespan of the brass casing by preventing fractures from gunpowder combustion. Eventually, the casings will still fail, as annealing can only repair the microstructure of the brass, not the macrostructure, and small deformations can grow massively between firings.
In this lab, we studied how mechanical properties of a metal are affected by cold working and annealing. The purpose of this lab is then to observe the changes of annealing temperature and time on the mechanical properties of a cold work cartridge brass sample. In other words, we'll determine the amount of time it takes to recrystallize the sample at a given temperature. And as we anneal at different times, we also perform grinding and polishing, etching, and do a metallography study on the sample. During grinding and polishing, we aim to achieve a mirror-like finish on the sample, so it's flat and clean. And during etching, we aim to expose features like grain boundaries, cracks, and uniformity on the sample. And later we'll do a metallography study by taking micrographs to identify features such as annealing twins, grain boundaries, and scratches.
Cartridge brass is the most commonly used brass alloy in the world. It has many useful applications due to its strength, ductility, and chemical resistance. Our sample was cold worked to about 55% by the TAs prior to our receiving them for further processing. A cold saw was used to cut smaller sections from the initial bar in preparation for heat treating. A coolant is circulated over the sample while a blade makes the cut. Speed and feed rates are optimized to allow cutting the samples without damage. Using the cold saw helps to maintain the microstructure created by cold working by minimizing localized heating in the metal. The sample pieces were washed to remove the coolant. They were then placed in a furnace at 450 degrees Celsius for times of 5, 10, 20, 30, 40, and 60 minutes. Varying the times in the furnace would allow us to investigate how hardness and average grain size varies with the amount of time in the furnace under annealing conditions. The samples were then removed in series as their soak times expired. The samples were allowed to cool on a fire brick at room temperature until they were cool enough to handle without protective gloves. Once the samples were cool, the hardness of each sample was tested using the indenter method. All measurements were recorded using the Rockwell B scale. The samples were then cleaned and prepared for mounting in epoxy. The proper amounts of Lecoset and binary reactants were weighed to ensure a quality polymer set that would be suitable for further processing. Mold rings were capped and sprayed with a Teflon release agent. A final check was performed of all components prior to the mixing of the polymer reactants. This was to ensure that everything was ready, as the epoxy has a relatively short working time. The components were finally assembled with the metal samples in the bottom of each mounting ring. The epoxy was then mixed and carefully poured into the mounting rings. The mounting rings, now containing the metal sample and liquid epoxy, were quickly moved to a pressure vessel. The vessel was sealed and the pressure increased to 35 psi by way of a high-tech, uncalibrated, manual bicycle tire pump. The pressure was monitored and adjusted as needed for the entire 5 minutes the sample was in the chamber. This increased pressure environment helped to minimize the size of the air bubbles in the Lecoset. Smaller bubbles helped to make polishing more even and provide better image quality of the polished samples under the microscope. For this experiment, you will need a series of platen polishers starting at 320 grit silicon carbide paper and progress through 600 grit silicon carbide, 6 micron diamond paste with green lubricant, 1 micron alumina suspension, and finish with 0.1 micron colloidal silica. After polishing, an ammonium hydroxide etchant as well as Clem's 3 reagent etchant will be used.
The procedure of this experiment is as follows. The samples are first heat treated. They were then cut and mounted in resin. The samples were then polished and etched and finally analyzed under an optical microscope. The mounted samples are then removed. They are grinded to remove excess resin. They are then polished using the previously mentioned grit papers in polishing suspensions. They are held to the polishing paper with medium even pressure and turned 90 degrees every minute until the polish is even. When polishing the sample with the 320 grit paper, make sure the surface is flat and scratches are uniform before moving on to the next grit size. The following polishing steps should take about 2 to 5 minutes each. Make sure to thoroughly clean the samples with soap water and isopropyl alcohol between polishing steps. However, after polishing with the 1 micron white label polishing paper with green lube and after polishing with the P-cloth with colloidal silica, make sure to sonicate the samples in clean isopropyl alcohol for 5 minutes to thoroughly clean the sample. The first etchant allows the grains to be visible. The second etchant will make the grains appear different colors under the microscope to distinguish them better. Between the etches, rinse the sample in distilled water. Do not over-etch the samples or images under the microscope will not be ideal. Once the samples are etched, the samples can be taken to the confocal microscope for imaging.
The first part of the results obtained and analyzed the hardness at different temperatures to understand the graphical curve and to observe where the recrystallization process occurs. On the left is the reference model and the right is the experimental, where it shows a reasonable resemblance. The recovery, recrystallization, and grain growth can be seen. In the procedure, we decided to choose 450 degrees Celsius as the point to conduct our annealing temperature with varying time, and as you can see, this falls in the middle of the recrystallization process. We hope to achieve a better understanding of how time affects the micrographs and grain size. So this is the data obtained for the grain size by utilizing the magnification in grains along randomly selected lines in order to follow the ACM standard formula. Conceptually, the longer time these samples are heated, the more likely it is for the grain boundaries to be consumed into larger grains, thus reducing the amount of defects but consequently reducing the strength. As seen, the data follows this relationship between time annealed and grain size until we reach 40-minute annealing time, where it was measured less. Perhaps this is due to the processing of the sample to begin with, where the metal was purer than previous samples, which would make it harder for the sample itself to recrystallize, thus a smaller grain size is seen. However, we can take a closer look on the next slide by observing the micrograph of it. As we see here, the image is quite interesting. There are a multitude of possibilities resulting in this feature, and keep in mind this is at 1,000 times magnification. First off, it is plausible that the sample had grit contaminants. After grit is used long enough, it becomes perceptible to accumulate to the object that is being polished. Thus, if this happened early on in the polishing cycle, it had time to cling to the surface where a cleaning solution would not be enough to rip it off. Another, less likely scenario could be allocated to an oxidation layer at the surface, but we did not see this on any other sample, so this is unlikely. When taking a look at the 60-minute sample, with reference to a similar noteworthy research paper that took a similar procedure to what we did in lab, the grains are similar in size and are rather large. This reference helps validate that the work we accomplished is of honorable mention and makes sense mathematically that these are the largest grains to the longest time annealed. The increase in grain size can allude to a reduction in hardness and strength, but enhancement to the ductility of the material, where cracks are less likely to form and propagate throughout the sample.
And with that, we're concluding our video. To remind you, recrystallization forms new grains, which decreases hardness and strength and increases the ductility of the material. This leads to a decrease in fractures, which is very important. We discussed how cold working and annealing affect mechanical properties. And lastly, we discussed changes in microstructure from etching as well as grinding, annealing, and metallography. Thanks for listening, and we hope you've enjoyed it.